Next, good morning. Today we will discuss procedure to draw the velocity diagram. Okay, velocity diagram is nothing but a velocity triangle. Okay, in the a triangle, velocity triangle. Okay, so the velocity triangle will be useful in analyzing different turbo machines. Okay, we can find what are the different forces acting on the turbine or power developed work output. Okay, these performance parameters we can obtain by making the analysis of velocity triangle. Okay, the velocity triangle consisting of three sides. Okay, which is made up of three velocity components. Those three velocity components are absolute velocity, relative velocity, tangential velocity of rotor. Okay, these are the three velocity components which will make the three sides of velocity triangle. Okay, absolute velocity of the fluid, relative velocity of the fluid, and tangential velocity of the rotor. Okay, see here, if you consider any stage of a turbo machine, it will be consisting of one row of stator and one row of rotor. Okay, that means if you consider any stage of a turbo machine, it is consisting of one row of stator and one row of rotor. Okay, the stator is a stationary element. The stator is a stationary element. The rotor is a rotating element, that is moving component. Okay, whatever the fluid velocity which is coming out of the stator, which is known as absolute velocity. Okay, why it is called absolute velocity means absolute velocity is nothing but the velocity of the fluid measured with respect to stationary object. Okay, here the stator is the stationary object. So whatever the velocity which is coming out of the stator, which is measured with respect to the stationary component, that's why it is known as absolute velocity. Okay, the fluid which enters the rotor, which is known as relative velocity, which is known as relative velocity. Why it is called relative velocity means that fluid velocity is measured with respect to moving object. Here the rotor is the moving object, moving component. Okay, so whatever the fluid velocity which enters the rotor, which is known as relative velocity. Okay, that is known as VR1, located by VR1. Okay, next the fluid velocity which leaves the rotor, that is known as VR, relative velocity at the outlet. Okay, why it is called relative velocity already I explained, because this fluid velocity measured with respect to moving component. Okay, similarly the fluid velocity which enters the stator, okay, that is also absolute velocity, okay, which is measured with respect to stationary object. Okay, next the rotor, which is having a rotating velocity, okay, which is having rotary velocity, okay, in a tangential direction. Okay, that is represented by u. U is nothing but tangential velocity of the rotor. Okay, now we need to write the velocity triangle. Okay, here I consider three locations. Okay, what are those three locations? One is at the inlet of the stator, that is represented as location 3, and this is the gap between the stator and rotor. Okay, this gap is either called as outlet of a stator or inlet of the rotor, represented by the location 1. Okay, next location, that is the outlet of the rotor, that is located as a. Okay, out of these three locations where we can draw the velocity triangle, that first we need to decide. Okay, so here we can draw the velocity triangle in the location where we will get all these three velocity components, because the three sides of velocity triangle will formed by these three velocities. Okay, there is absolute velocity, relative velocity, tangential velocity of the rotor. Okay, in whatever the location we will select to draw the velocity triangle, there we need to get these three velocity components. Okay, suppose if you want to draw the velocity triangle here, okay, can we have all the three velocity components here? No. So here only one velocity component we will get. What is that? That is the absolute velocity of the fluid which enters the stator. That is V3. The location V represented as V3. Okay. Only one velocity component we will get at this location. What is that? Absolute velocity. We won't get the relative velocity. Okay, because there is no moving object here to get the relative velocity, and also we won't get the tangential velocity of the rotor because there is no moving object here. This is the stationary. Understood? We cannot draw the velocity triangle at the inlet of the stator. Understood? Okay. Next, in the location 1, can we able to draw the velocity triangle? Okay. Can we get all these three velocity components? Yeah, we will get it. See here, whatever the velocity which is coming out of the stator, that is absolute velocity. Okay. The velocity which enters the rotor. Okay. What is that? Relative velocity. VR1. Okay. And also this rotor is possessing the velocity. Okay. That is tangential velocity. Okay. And that is represented as U1 at the inlet. Okay. The tangential velocity of the rotor at inlet is represented as U1. Okay. At this location, we will get all the three velocity components: absolute velocity, relative velocity, and the tangential velocity of the rotor. Okay. So we can draw the velocity triangle at location 1. Location 1 means that is the gap between the stator and rotor. Okay. This location can be defined as inlet of the rotor. This is the inlet of the rotor. Okay. Then how to draw the velocity triangle at the location 1? Okay. See, first we will have the V1. This is V1. Okay. Next, we have the tangential velocity of the rotor. This direction. At inlet, we will represent it as U1. Okay. Then what is the direction of VR1? Okay. See here, the direction of the VR1 should follow the law, that is vector law. Vector V is equal to vector U plus vector VR. This is the key rule we follow to complete the velocity triangle. Okay, this is the vector. That means whatever the velocities are there here, these velocities we will consider as a vector quantity. Okay, what is the meaning of vector? It will be having both magnitude and direction. Is it right? To complete the velocity triangle here. Okay, here we don't know the direction of VR1. Okay, so we have to complete the velocity triangle here. Is it right? Okay, for that we follow the key rule. That is vector rule. The vector V is equal to vector U plus vector VR. Okay, see here. That means the product and direction, the magnitude and direction of V should be equal to the magnitude and direction of VR plus U. Okay. See here, if you draw the VR here, what is the direction? The direction should be like this or like this. And it should be downward. This is the direction. That means vector V is equal to vector VR plus U. Okay. This is the velocity triangle. Okay. Either you can draw like this way also. See, this is acute triangle. In the form of obtuse triangle also you can draw like this. V1, U1, VR. Like this way also you can draw. Otherwise, you can draw like this way also. Say this is V1. Instead of drawing the U in the bottom, you can draw here also. U1. Okay. Then what is the direction of VR? What is the direction of VR? Follow the cue. Vector V is equal to vector U plus VR. Okay. So this is the VR. Okay, like this also you can draw. In any form, you can draw the velocity triangle. Understood? Okay. Next, in the location 2, that is at the rotate of the rotor. Okay. Can we draw the velocity triangle? See here also you get all the three velocity components. See here. See here you can have one more stage. Okay, this is a single stage. If you consider any single stage of a turbo machine, it will be consisting of one row of stator and one row of rotor. Okay. If you have a second stage, that is in multi-stage turbines. Okay. What is the structure? Will be repeat here. Stator, next rotor. That means here you are having a stator here. Okay. Whatever the fluid which enters the stator, that is absolute velocity. Okay. Located as V2, represented as V2. Is it right? So once again, here we have the relative velocity which leaves the rotor, the absolute velocity which enters the stator, or we will be having the tangential velocity of the rotor U. Okay. Or else, if you have a single stage, okay, then see whatever the fluid which leaves the stage, that means the fluid which is coming out of the machine, okay, that will be considered as absolute velocity only. Okay, this velocity is also measured with respect to the stationary object, that is observer. Okay, when the fluid is coming out of the machine. Okay, so here we will be having the absolute velocity which is exiting from the machine and which enters the stator of a second stage. Okay, so here also you can draw a velocity triangle. Okay, you will be having three velocity components. That is absolute velocity, relative velocity, and tangential velocity of the rotor. Okay. Yes. What is the velocity triangle here? Here VR2. This is the direction of VR2. The direction of U2. Here outlet. At the outlet, what is the tangential velocity we are having? U2. Okay. This is U2. Then what is the direction of V2? What is the direction of V2? By this Q. See here, VR2 plus U2 is equal to V2. Now, okay, this is V2. Okay, V2 is equal to VR2 plus U2. Or the same thing you can write like this way also. In a fused triangle. This is acute triangle, or yeah, only two methods you can draw, because if you draw the U2 like this, the directions will change us. Okay, this Q will not apply. Okay, these two will be in opposite directions. Okay, you cannot take it upside. Okay, you have to take U2 in the downside only. Okay, either you can draw like this or like this. Understood? Okay. This is the outlet velocity triangle. This velocity triangle we call it as a inlet velocity triangle. This is outlet velocity triangle. This is inlet velocity triangle. This is outlet velocity triangle. The inlet and outlet will be defined with respect to the rotor. Okay. See, we won't define it with respect to the stator. Here, inlet and outlet will be defined with respect to the rotor. Okay. The inlet means that is inlet to the rotor. That is the location 1. Outlet means that is with respect to rotor. That is location 2 at the outlet of the rotor. Okay. This is the inlet velocity triangle. This is the outlet velocity triangle. Understood? Okay. Yes. Note down. As well, deriving the Euler's turbine equation, we discussed that whatever the absolute velocity is there, that will be resolved into 3 components. What are those? One is axial velocity component. Second, radial velocity component. Tangential velocity component. Okay, if you consider any machine, we will have only 2 velocity components. For example, if it is an axial flow machine, you will be having axial velocity component and tangential velocity component. Okay, if you consider radial machine, radial flow machine, you will be having radial velocity, tangential velocity. Okay. See here, the tangential velocity component we call it as a wave velocity. Wave velocity. And this axial velocity and radial velocity we call it as a flow velocity. Say here, axial velocity component in case of axial flow machines, radial velocity component in case of radial flow machines, which is known as flow velocity. That means the absolute velocity, whatever the absolute velocity striking the rotor, which has to cause the rotation of the wheel and also which has to carry out the flow from inlet to the outlet. Is it right? When the absolute velocity strikes the rotor, okay, which has to touch the wheel and also which carry the flow from inlet to outlet. Okay, whichever the velocity component which causes the rotation of the wheel, that is the wheel velocity. That is nothing but tangential velocity component. Okay, whichever the velocity component which carries the flow from inlet to outlet. Okay, that is known as flow velocity. That is axial velocity component in case of axial flow machines, radial velocity component in case of radial flow machines. Understood? Okay. Now we have to resolve this absolute velocity into 2 velocity components. That is, one is flow velocity component, another is wave velocity component. Understood? Okay. See, now we will modify this velocity triangle in order to show the flow velocity component and wave velocity component. Okay. Say first, I will consider the inlet velocity triangle. This is V1. This is VR1. This is U1. Okay. Now we have to resolve this absolute velocity into 2 components. That is wave velocity and flow velocity. Wave velocity represented by VU. Flow velocity represented by VF. Okay. Let's see how to resolve the forces. If it is xy direction, let it be this is the force V1. How you resolve the forces in x-axis and y-axis in mechanics? So here, this is Vx and this is Vy. Is it right? Okay. The two forces we resolve. One is along x-axis, another is along y-axis. Is it right? Okay. See, instead of writing this Vy here, I will shift to here. Okay. This is Vy. Vy. Okay. This completes the velocity triangle. Is it right? That means here Vy, this is the flow velocity represented as Vf in general. Okay. If it is an axial flow machine, that is represented as Va, axial velocity component for axial flow machine. Okay. If it is a radial flow machine, represented as Vm. Okay. This Vx is their length. That is wave velocity represented as Ve. Okay, so by resolving absolute velocity, one is along axial direction for axial flow machines and radial direction in case of radial flow machines, represented as Vf1 flow velocity, and this is tangential velocity, that is Vu1. Okay. Now we have to show these two components here. Okay. How to show it? See here. What is this? Vu1, wave velocity, a tangential velocity component. What is this? Vf1, flow velocity. Okay, this is the velocity triangle, complete velocity triangle by showing absolute velocity, relative velocity, tangential velocity, and also the velocity components of absolute velocity, that is flow velocity and wave velocity. Understood? Okay. Now here we will be having the angles. Okay. Say this is alpha 1 and this is beta 1. Okay. What is this alpha 1? Alpha 1 is nothing but the angle made by the absolute velocity with respect to tangential direction. Okay, this is alpha 1. Okay, this is also known as nozzle angle. Nozzle angle at the inlet of the rotor. Nozzle angle at the inlet of the rotor. That is the tip of the nozzle, whatever the angle made by the tip of the nozzle with respect to tangential direction. Okay, these are the tangential directions. Okay, the vertical will be axial direction for axial flow machines, radial direction for radial flow machines. Understood? Okay. So here VR1, whatever the fluid velocity, the angle made by the fluid velocity by entering the rotor, this is the beta 1. Okay, this is known as rotor angle at the inlet. Okay, rotor tip angle at the inlet of the rotor, that is known as beta 1. Okay, similarly here we have the angle made by the relative velocity when it leaves the rotor. What is this? This is beta 2. Okay, this is known as rotor angle at the outlet. Beta 2 is known as the rotor angle at the outlet. Okay. Similarly, whatever the absolute velocity which leaves the machine or which enters the next row stator. Okay, that is known as alpha. Okay, so here these angles we will take here, alpha 1 and beta. Okay, this is the inlet velocity triangle by considering flow velocity and wave velocity also. Okay, similarly for outlet velocity triangle, we need to draw. This is the outlet velocity triangle I consider. VR2, U2, V2. Okay. VR2, U2, that is equal to V. Is it right? Here also, absolute velocity should be resolved into two components. One is along axial or radial direction, another is along tangential direction. That is flow velocity and wind velocity. Okay. Yes, how to resolve it? Say this is the V2 you are having. Okay. Resolve along x-axis and y-axis. What you are going to get? This is Vx and this is Vy. Okay. This Vy will be shifted to here. Sorry, this Vx will be shifted to here. Okay. This Vx is equal to Vu2. This Vy is equal to Vf2 or Va2 or Vm2. Okay. Same thing we will be write it here. Okay. What you are going to get? This is Vf2 and this is Vu. Okay, wave velocity component for V2, flow velocity component for V2. Understood? Okay. What are these angles? This is alpha 2 and this is beta. Okay. This is the outlet velocity triangle. This is the inlet velocity triangle. Understood? Okay. Any doubt here? Okay. So these are the what we call generalized velocity triangles. Okay, we are going to use these velocity triangles in future also. Okay, nice. Okay.